Okay, we will now investigate the relationship between the range and kernel of an operator and its adjoint. Okay, so we have the following proposition. So let V and W be Banach and A from dA contained in V taking values in W densely defined linear operator. So we set G equals G of A, the graph of A. This is a subspace of V cross W, and H, so set H equals V cross 0, again contained in V cross W. So these are subspaces. Okay, then 1 n of A cross 0 equals G intersection H. 2 V cross the range of A equals G plus H. 3 0 cross n of A star equals G perp intersection H perp. And 4 range of A star cross W star equals G perp plus H perp. Okay, this is almost an immediate thing, so proof. So let us first consider G intersection H. So H has the second coordinate 0, so G intersection H will be something cross 0, that is clear. Now what is in G? The first coordinate is the domain of A, and the second coordinate, if it has to be 0, then this has to be the null space of A. So that's why we get that. So okay, now secondly for G plus H. So if you take G plus H, so the second coordinate has 0 in H, and so if you add anything you will only get the second coordinate of GA, and that is in the range of A. So you will get, so G plus H will be something cross range of A, and the first coordinate in H is V, so whatever you add to it you will only get V, so you will get V cross range of A. So similarly 0 cross n, so you do the other two yourself, only you use the fact J of G of A star equals GA perp. You must remember this relationship, and in the same way you can do 3 and 4. Okay, so that is this proposition. Okay, so while we are here, let me note down some of the old results which we did, which we will be using. Okay, so if G and H closed subspaces of a Banach space V, then you have G intersection H equals G perp plus H perp perp, and G perp intersection H perp equals G plus H perp. These we did when we were in the annihilator section. And then you have from these two, if you take the perp again, G intersection H perp will contain G perp plus H perp closure, and G perp intersection H perp will be G plus H closure. Okay, and then we also had a theorem which says that the following are equivalent. the following are equivalent. You have that G plus H is closed, G perp plus H perp is closed, and then G plus H equals G perp intersection H perp and G perp plus H perp equals G intersection H perp. Okay, this is another theorem which we prove. Okay, so let us just keep that in mind, so that okay. So now we have corollary to the previous proposition. So V and W Banach and A from D of A contained in V taking values in W, densely defined and closed. So we are adding another hypothesis. Then N of A equals range of A star perp, N of A star equals range of A perp, N of A perp contains range of A star closure, and N of A star perp equals range of A closure. Okay. So the last two relationship, if you take N of A perp, that will be range of A star perp perp, that's in a dual space, so that should contain the range of A star closure. Okay. Then N of A star perp is range of A perp perp, and this is in the basic space, and therefore it will be range of A star, range of A closure. Okay. So these two conditions, they follow from the first two, and therefore we will need not. So we only have to prove the first one. Okay. So proof. So as usual, let us take G equals G of A contained in V cross W, and H equals V cross 0 as before, contained in V cross W. Okay. So then we already saw what was one of the relationships we saw. We saw that G intersection H is G perp plus H perp perp, that relationship here. So we have G intersection H equals G perp plus H perp perp. Now what is G intersection H? G intersection H is NA cross 0, and therefore we have here NA cross 0 equals G perp plus H perp perp. G perp plus H perp is range of A star cross W star. So if you take the perp, the W star will give you 0, and here you have range of A star perp. And then if you just compare this, you get the first relationship, namely N of A equals range of A star perp. Similarly, you have G perp plus H perp intersection H perp. G perp intersection H perp equals G plus H perp. So G perp intersection H perp equals G plus H perp. So what is G perp intersection H perp? That is 0 cross NA star equals G plus H perp. G plus H is V cross RA, so the perp of it will be 0 cross RA perp. And therefore you have N of A star equals RA perp. That proves the second part of the proposition. Okay. So we have a relationship, the null space of an operator is nothing but the orthogonal annihilator of the range of the adjoint. Similarly, the null space of the adjoint is nothing but the annihilator of the range of the original operator. Okay, so this is a connection between the two. Okay, now we have a little more. So, theorem BW Banach and A from D of A contained in V taking values in W, which is closed and densely defined. So the previous corollary is true, so in particular. Then the following are equivalent. One, range of A is closed. 2, range of A star is closed. So this range of A is closed in W, range of A star is closed in V star. And then 3, range of A equals N of A star perp, and 4, range of A star is N of A perp. Okay, so now if you look at the G and H definitions which we have given before, G equals GA, H equals V cross 0, and then we had various relationships between the two in this particular corollary. So if you go back and check all this, then this statement range of A closed is the same as saying G plus H is closed in V cross W, because what is G plus H? V cross range of A. So if this is closed, then the product is closed, and therefore you have that. So in the same way, this will be saying that G perp plus H perp is closed in V star cross W star. And then the third one is saying that G plus H equals G perp intersection H perp perp, and the fourth one is saying G perp plus H perp equals G intersection H perp. But this theorem we have already shown. The following are equivalent. So we have these 4 statements here, and that is exactly what we had earlier. So that completes the proof. There is no need to prove it again. Okay. Now remark, of course, all these theorems are naturally true for continuous linear operators because they are automatically closed, densely defined because they are defined everywhere. In particular, so if you take so remark again, suppose VW finite dimensional, then all operators are continuous linear operators, all subspaces are closed, and this is so we have that the range of A equals null space of A star perp. This is called the usual Fredholm alternative. And for instance, if you want to solve the equation Ax equals B, where A is a matrix, say m by n matrix. So when will this have a solution? So let us assume that A star y equal to 0. Okay. Then if you take y-ax, so take the inner product yb, this is y-ax, by definition this is A star y x. Here the duality bracket is the same as the inner product in finite dimensional spaces, and then this is 0. Okay. So if B belongs to range of A, this implies that B belongs to null space of A star perp. Okay. And then by a dimension argument you can show this, in fact it works both ways, and therefore you have this Fredholm alternative. So the kernel annihilator of the kernel of the adjoint is precisely the range. So this is in fact the compatibility condition that B must satisfy in order that this equation has a solution. So this equation has solution if B is in the range of A, and for that it needs to satisfy some condition, and that's precisely saying that yb equal to 0 for every A star y equal to 0. So that is, and that result is called the Fredholm alternative. Finally, we have a theorem on surjective maps. So theorem, this is a very nice theorem. So we say that VW Banach and A from V dA of to W closed and densely defined. The following are equivalent. One, A is on 2. So when is a map surjective? Okay, so that means range of A equals all of W. Okay. 2, there exists a constant C such that for all V in dA star we have norm V in W star is less than or equal to C times norm of A star B in V star. So such a map is called bounded below. A star is bounded below. That means you have a constant going in the opposite of the usual thing. You have norm A. Bounded means norm of A star B less than C times norm B, but here you are having norm of A star B bigger than a constant times norm B, and that is called bounded below. 3, you have that null space of A star is 0 and range of A star is closed. So these are characterizations of a surjective map. So once you have a surjective map, that means you can solve equations. That is the important thing, why we are interested in such things. So proof, let us prove that 1 implies 3. So A is on 2, so range of A is W and hence closed. So we can apply the previous theorem because you have closed bounded operators. So range of A is closed, so you have so many things. So range of A star will be NA perp. And in fact range of A star will be closed. So range of A closed implies range of A star is closed. And you also have N of A star is range of A perp. And since range of A is all of W, that we have proved even much before, N of A star is range of A perp, and therefore and since range of A is the whole of W, this has to be 0. So this proves 3. Range of A star is closed, and this. So let's say 3 implies 1. That means n of A star is 0 and range of A closed. Range of A star. So then you have range of A equals n of A star perp by the previous theorem. Range of A is n of A star perp, that's number 3, and therefore n of A star is 0, and therefore this has to be W. Okay, so implies A on 2. So we have proved that, so thus 1 is equivalent to 3. So now we want to show that 2 and 3 are also equivalent. So the condition that norm A star V is greater or equal to C times norm V for all V in dA star. So if A star V is 0, automatically this means, so A star V equal to 0 implies V equal to 0. So this implies that null space of A star is singleton 0. Okay, and then let us take a sequence Vn in dA star such that A star Vn goes to F in V star. Then again by the boundedness below, we have norm Vn minus Vm is less than or equal to C times norm A star Vn minus A star Vm. This is Cauchy, so implies Vn is Cauchy. We are in the Banach space, so Vn converges to some V, A star Vn converges to some F, and therefore A star is closed. This is always true, and therefore this implies that V belongs to dA star and A star V equal to F. Therefore, if A star V n goes to some F, F is equal to A star V, so this implies F belongs to dA star, range of A star, that is range of A star is closed. Okay, so then finally, so this proves 3 completely. So now we want to show 3 implies 2. So we go back to the notation which we had earlier about G and H. G equals G of A, H equals V cross 0, and then we have that n of A star equal to 0 implies that G perp intersection H perp is 0. Okay, so because what is G perp intersection H perp, we computed it somewhere. G perp intersection H perp number 3 is 0 cross NA star. If NA star is 0, then G perp intersection H perp is in fact 0. So we have that. So then, and you also have that range of A star closed implies G perp plus H perp is closed. Again, what is G perp plus H perp? G perp plus H perp is range of A star cross W star. So if number 4, and therefore if range of A star is closed, you have that G perp plus H perp is closed. So we are in the situation where the sum of two closed subspaces is closed and the intersection is 0. So this is in fact a direct sum. So then by a proposition which we proved by the open mapping theorem, there exists a C such that if you have Z in G perp plus H perp, then Z is equal to A plus B, A in G perp, B in H perp, and norm A less than equal to C times norm Z, and norm B is less than equal to C times norm Z. When you have two subspaces, you have this. But now, since G perp intersection H perp is 0, in fact A and B are unique. There is no choice of decomposition, there is only one decomposition available. So if we find it, that is the correct one, and it will automatically satisfy the condition. So let us take V in dA star. Okay. Then you said Z equals A star B comma 0. So this belongs to range of A star cross W star, which is in, as we know, G perp plus H perp. Okay. So now let A equals A star V comma minus V. Well, if you took minus V A star V, this will be nothing but J of A star VV, sorry, V no, sorry. Okay. Sorry, okay, this is wrong. So take A star V minus V, okay. So this, if you had taken minus A star V, this belongs to J of GA star. But GA star is a subspace, so this also, which is equal to GA perp. But then minus of this will also be in GA perp because that's a subspace, so this belongs to GA perp or G perp. Okay. Now you take B equals 0V and automatically that belongs to H perp. Okay, and then you just add, you get A plus B is A star B0, which is equal to Z, and therefore you have those two inequalities. So in particular you have that B is less than or equal to norm B is less than or equal to C times norm Z, and that tells you that norm V is less than or equal to C times norm of A star, and that proves the remaining thing. So this completes the proof. Okay, fine. So similar remark, similar statement, similar theorem can be stated and proved. For surjectivity of A star. Okay, you can try it as an exercise, it's just identical, so you can go ahead. So now if you look at another remark, let us take V and W finite dimensional. then everything, as I said, is a continuous linear operator, in particular closed, densely defined, everything, and therefore you have that A is onto if and only if A star is 1 1, because we have the range equals null space of A star perp. Okay, so and this is equal, so you have, similarly A star onto if and only if A is 1 1. But here in infinite dimensions we have do not have, so here why is this true? Because the range is always closed, because in finite dimensional range is always closed. That is why these theorems work, but in infinite dimensions the range need not be closed, and therefore infinite dimensions range need not be closed. Range of say A. Okay. So you can only say from the above theorem that A is onto implies A star is 1 1, and then A star onto implies A is 1 1. You can't go back and say the thing, unlike in the finite dimensional case. Let us take an example. Let V equal to W equals little l2. Again, remember, these are sequences which are square integrable, and therefore you have L2 star is the same as L2, and we know what is the duality bracket. It is just the usual inner product. So let us take AX equals x1, x2 by 2, x3 by 3, and so on, xn by n. Okay, so then you can check A equals A star. So this operator, and then clearly A is 1 1, but A is not on, because what is the range? The range of A is set of all x in L2 such that x, so this is the range, means it must be n times this must, so if you let us say y in L2 to be clearer. So we have yi equals xi by n, where x is in L2 and y is also in L2. Okay, so you have xi is n times yi, so this is sigma n square yi square should also be finite. So this is a very stringent requirement. So this is the range of A, so this is not an onto map. Okay, and then you can also check that the range is not a closed set. Okay, so with this we complete this chapter, and we will do some exercises next.